Recall the example that we did on the last video when we first introduced what it meant for a sequence of functions to converge pointwise to its limiting function f. So we use these functions. Fn was defined to be x to the n. So f1, for example, is the function f of x equals x. f2 would be the function x squared. f3 would be the function x cubed, etc. And we proved that this function converges pointwise to a piecewise function. And so I've drawn the piecewise function. I've drawn a couple of the first few functions from our sequence, and then I've drawn the piecewise function that you get here in red. Notice that each of the functions we're working with in our sequence, so like here's y equals x, that's f1. Then y equals x squared is f2. And we've got f3, f4. Something weird going on here is that each of these functions in our sequence is continuous. It's just a polynomial. It's a power of x. However, what we see is the function that it converges to is not a continuous function. So here we began with continuity, so we had each fn was continuous, but we resulted in the limiting function not being continuous. And this kind of begs the question, well, what went wrong? Why didn't the limit have to inherit the continuity of the sequence of functions itself? And that's going to be what we investigate today in this video. Before we get started looking at the details of exactly why f fails to be continuous here, I want to point something out or just remind you so that you have this in your mind as we're going through the rest of the video. It's really important to remember that when you have pointwise convergence, what that means is you fix your x first and then you choose your capital N. So you're actually, as you look at a different x value in your domain, the tail that you need to guarantee convergence is going to vary. So it's really important to remember here, in pointwise convergence, capital N can depend on x. So it may be that as I change the location that I'm looking at convergence for, it may be that I need to change my value of capital N. And that's the case in this picture here. I'm going to show you what I mean by varying x. So we've claimed and we've proven that when we're dealing with x values that are strictly less than 1, we know that our functions are converging to zero, the function y equals 0. So thinking about this as a convergence picture, remember what that means. We're trying to choose a capital N. We're trying to make n large enough so that we can guarantee that our function falls inside the epsilon band for each function in the tail of our sequence of functions. So, all right, so I'm going to take a couple different x values. So I'm going to say, all right, let's look at this x value, for example. I'll call that x1. Then we'll look at, say, this x value, which is x2. And then I'm going to look at x3 over here. So if I talk about x1 and I fix that value and I generate the sequence of outputs that I get from plugging that into f1, f2, f3, then what I'm doing is I'm getting points on the curve that essentially are associated with that vertical x value. And same thing with x2. When I plug in x2 into f1, I'm going to get this point, then I'm going to get this one. When I plug into f2, f3 is going to give me this point, etc. And then finally, I can do the same thing over here. Notice my points are significantly higher on the graph. So what this is actually showing me, when I pay attention to just the vertical line associated with x1, So we're going to zoom in here. I noticed that all of my points, like all of the points that I'm plotting on my sequence, actually even beginning for F1, those are all in my epsilon band of 0. This tells me that I could choose capital N to be 1 at this value, and I would meet my epsilon constraints. Every single function in the sequence produces a value in my epsilon band, and so therefore I don't actually have to go out in my tail at all. I can just say, well, capital N equals 1 works for x1. So let's write that down. So since all Fn of x1 are in the epsilon of the number 0, we may choose capital N. I'm going to call this capital N1. Well, actually, here, I'll just leave it as capital N. This is going to be equal to 1 for x1 when we're trying to prove pointwise convergence. Then I want to look at, well, what happens with x2? So I'm going to zoom in again on that. And what we see here is that f1 of x2 is outside the band, f2 is outside the band, but it looks like f3 is inside the band, and then any function will be lower than that later in the sequence. So this is telling me that I couldn't make a choice of n equals 1 for this particular location. Instead, we want to choose capital N to be equal to 3 for x2, and that's what we need in order to guarantee that Fn, this is to guarantee Fn of x2 is in our epsilon band of 0 when n is greater than or equal to capital N. And then finally, we can do the same thing for x3, but notice that I don't even have enough functions plotted here. None of my points that I have, none of my corresponding values in my sequence are actually inside this band. It looks like we're going to have to go even further out. So what I want to point out here is that we need capital N larger than 4 at least to get Fn of x3 to be in our epsilon band of 0 when n is greater than or equal to greater than or equal to capital N. What I'm trying to point out here is that capital N is going to have to increase. Capital N gets larger as x moves toward 1. So different n's, we need to choose different capital N's. As x approaches 1. Okay, so I want you to keep that in mind as we investigate what exactly went wrong, what condition I would need instead if I wanted to guarantee that convergence of a sequence of continuous functions would result in a continuous limit. So recall the definition of what it would mean for f to be continuous at C and A, and we're going to try to take a closer look at why this definition fails. Even though we have pointwise convergence for our specific example. So remember, proving continuity is all about you specify an epsilon neighborhood and you try to find the delta neighborhood such that when you grab inputs from the delta neighborhood, the outputs have to fall in an epsilon neighborhood of the function output at C. So when we're trying to prove this, remember how we focus on what we focus on. We focus on this expression here. We're trying to say, well, how is f of x minus f of c as a distance? How is that size related to the given information? because it's all about finding those connections so that you can make certain choices to try to meet that constraint, being less than epsilon. So we want to take a look at our given information and then kind of ask ourselves, well, why did we lose the ability to control the size of f of x minus f of c, even though we had pointwise convergence and continuity on the original sequence of functions? So we're asking the question, how is f of x minus f of c, so the distance between those output values, related to the given info? And when I say given info here, I just mean, one, we know that each Fn is continuous. And two, we know that Fn converges to F pointwise. And so each of these facts that I have has a expression associated with it whose size can be controlled. And so when I say that Fn is continuous, I know that I'm going to be able to make the expression Fn of x minus Fn of c. I'm supposed to be able to make that less than whatever we want. I'm going to choose a delta neighborhood that makes that constraint. And then for pointwise convergence, we know that that says you can take a value x, so you pick x in your domain, and we're looking for Fn of x minus f of x, our limiting function. That should be less than whatever we want. We can make choices on capital N, given an arbitrary x, in order to do that. So what we need to do is we need to take each of these expressions that we just wrote out, that we know we can make small, and see whether or not we can figure out how the size of those expressions is actually related to the expression that we would need to have small if we were proving continuity. So this is going to be a classic triangle inequality type argument, where I'm going to take f of x minus f of c, and I'm going to try to relate that. I'm going to add and subtract terms in the form of 0 so that I can change this expression to see how it's related to the two expressions that I know I have control over. So looking at this, I first notice I've got f of x. The only thing that I have related to f of x here in my given information is I can relate using pointwise convergence. I know that how Fn can be made close to f of x. So I'm going to start by taking f of x. I'm going to subtract Fn of x, and I'm going to add Fn of x, just so I'm not changing the value of anything. I'm just changing the way that it looks. Then using the triangle inequality, I know that I can split this up, and that's going to give me f of x minus Fn of x plus Fn of x minus f of c. And I take a step back and I look at this and I say, well, do I have expressions now that I have control over? So I look at this first expression. It's f of x minus Fn of x. That's actually the same. If I call this here, I'll call this expression 2 up here. That's the same as 2. It's just the subtraction is in a different order, but that's okay because we've got absolute values. But when I go to look at my second piece, I need to relate Fn of x to f of c. And so I go up and I look at, well, what did I get from my expression 1? Well, that only tells me what happens when I'm looking at x and c being evaluated in the same function, Fn. But here I've got two different functions. I've got Fn, and then I've got f. And so right now we should be asking the question, well, how's this going to work? I don't have the ability to handle that term. Can I add and subtract something so that I can create a relationship that looks similar to the first piece of given information that we have from each fn being continuous? Well, I can just add and subtract fn of c in that last expression. So I'm going to say this is really equal to f of x minus fn of x plus, now I'm going to say fn of x minus fn of c. The reason I'm doing that is because that matches expression 1, and I would like to be able to use that information. And then I need to add it back in so that I'm not changing the value of my function, or of my expression. And then I can split this up using the triangle inequality. Okay, so now I need to take a step back and say, how do I control the size of each of these expressions? So this first expression, we already said what to do with that. That comes from the fact we get to use the fact that fn is converging to f pointwise. This next expression, that now matches what it means. We can make that expression small using the fact that fn is continuous. So here this is using fn continuous at c. And then our final expression looks pretty similar to it looks really similar to pointwise convergence, except rather than working with an arbitrary x, we're looking specifically at the value x equals c. Now that's okay, because pointwise convergence says fix x first, or choose your value of x first and then look at convergence. So this is saying fn converges to f pointwise. We have control over this specifically, when x equals c. So now we know how the expression f of x minus f of c is going to depend on the expressions associated with each of the given information. What we need to do is we need to actually go through and ask ourselves, okay, each of these expressions that we've highlighted, we know we can make small, but what are the conditions, what are the constraints that have to be in place in order to use the fact that these are small? Some of them require choosing delta neighborhoods, some of them require choosing capital N's. We want to take a look at what all of our different requirements are and then ask ourselves, is it possible to meet all of those constraints at the same time so that each of these three expressions can be made small, less than epsilon over 3, so that when we add it together, our overall distance between f of x and f of c is less than epsilon. So let's make some high-level notes here about how we make our choices for each of these three expressions to make them small according to our definitions. So this first one, we said we can make this small because of pointwise convergence at x. So we want to think about how that process works. In order to make this expression actually small, what you do is you fix x first, and then you find the capital N that works for convergence. In this next expression, this is coming from continuity. So here, notice that we're using Fn being continuous at C. So that means that I am first fixing which value of little n I'm talking about, my Fn, and then I'm going to get my delta neighborhood that allows me to say any x in that delta neighborhood means f of Fn is going to meet the output constraint. So this is going to say what I have to do first is I'm fixing what little n I'm talking about. Because as I change what little n is, I'm getting a different function, which means I have a different continuity constraint. So we fix n, then we find delta, And then from there, we get x in the delta neighborhood. Those are the only x's we're concerned with in that case. So we don't really so much have a choice over what our x is. We're choosing delta, and then that determines which axis we're looking at. And then this final expression is, again, pointwise convergence, except this time we've actually just gone ahead and said we're looking at the specific point x equals c. So really what we're doing is we're saying fix x equal to c, and then find capital N specifically for that c value. So we need to go through and we need to ask ourselves, are we going to have any kind of circular argument coming out here? Does getting our constraints, the order in which we fix our variables, is that going to result in a circular argument at any place? Can we actually do all three of these things simultaneously? I'm going to call this condition here, in the first one, I'm going to call this condition I, or 1. And then I'm going to call this other one condition 2, and then the third one is condition 3. And I want to look at what we are required to do here in each of these. So the first condition says, as we change x, n must change. Capital N must change. This is consistent with, remember our picture up here when we had x1, x2, and x3. As we changed which x value we were looking at, we said that led to us needing to choose larger values of capital N. Okay, so that's what we got from the first one. Now let's look at what 2 says. So notice we're picking our n first. So this is telling us that as we change which n value we're looking at, we have a different function, which means we're going to have a different way that we're looking for the delta neighborhood, for the definition of continuity for that very specific fixed function in your sequence. So this is telling us that as we change little n, but ultimately remember what controls little n is capital N. So as we change capital N, delta must change, which transitively says that x changes. Because remember, when you pick your delta, you then have to handle all x values inside that delta neighborhood. So as delta changes, the x's you're looking at will also change. So delta must change, which transitively says the x's we are considering in the delta neighborhood are changing. Now, 3 is just kind of, condition 3 I'm not going to bother to write down because 3 is just a special case of 1 where I am picking the particular x value to be the point C. But let's take a look at this, and actually I would encourage you to pause your video and think on your own and ask yourself, is there anything circular going on here in our argument? Well, what we're saying here in this first statement is we are saying capital N depends on x. But in the second statement, we are saying, now that I have a new n, I'm going to get a different delta, and that's going to change my x. So as we change capital N, we get a different delta, and then we get a different x. So here what we've really said is n depends on x, which depends on n. The way I'm getting that, n depending on x, that's coming from statement 1. X depending on capital N is coming from statement 2, because you fix your capital N, that gives you delta, delta gives you your x. So fix N first, then get x. Now what we have is a circular argument. We need to be able to fix our x and choose an n, but notice that as soon as you choose an n, the x's you're working with have to change. So this is circular. What that tells us is that we may not be able to do this. We may not be able to do this if capital N varies as x changes. And this is getting at the heart of why pointwise convergence is actually not good enough. So the issue that we have now exploited is that pointwise convergence allows capital N to change as x changes. So therefore, what we've been able to say is that if each Fn is continuous and Fn converges to F pointwise, F may not be continuous. We don't know. We don't have that kind of control based on the calculations we were just looking at. And the example that we had is Fn being x to the n. So we ended up having this circular argument. And what this comes down to, again, is the fact that n can change as x does. We actually need the same capital N to work for all x. And we've seen this type of idea before where we were saying we want the same thing to work for all values. What we saw was uniform continuity. So let's recall what we know, because maybe that'll give us some insight into what constraints we should add to our equation so that having continuity, the sequence of functions, and then having some type of convergence would actually mean that the limiting function f has to inherit continuity as well. So we've seen this idea before. Remember in the case of continuity, what we said was, oh, fix your C that you're looking at, then get delta. But in uniform continuity, the same delta works for all C. So what we have analogously is when Fn converges to F pointwise, we fix x, then get capital N. What we would like is for the same capital N to work for all x, and that is going to be our definition of uniform convergence. So we can say that Fn converges to F uniformly, and I will write down the official definition here, but what we would like to happen here is we want the same capital N to work for all x. So now we have the necessity of introducing a new type of convergence of a sequence of functions. So you can do convergence by fixing an x in your sequence and then just thinking about it as regular pointwise convergence, or you can require the following. So we're going to define each Fn to map from the domain A to R. The sequence Fn converges uniformly on A So remember how uniform continuity, it was it had to be on a set. Same thing works here because we're going to be talking about a set of values for which the same capital N works for all of those values. And it's going to converge to F, which is also a function with domain A, provided, well, here we need to make our definition such that we choose our capital N before we look at X. So what we're going to do is we're going to say for all epsilon greater than 0, we want to get our capital N before we even introduce X. So there has to exist a capital N such that for all X in A, and for all little n greater than or equal to capital N, Fn of x minus f of x is less than epsilon. So notice the big difference here in uniform convergence. It's the placement of for all x in A. In pointwise convergence placed that value here, or this quantification here. That pointwise would put you introducing x first before you pick your n. But in our case, we are now going to choose our capital N first. So here, the same capital N must work for all x. And that is the big difference in uniform convergence. This says in. Okay. So now we actually have two types of notation, we have this notation that actually can denote either type of convergence. So the notation for uniform convergence is still Fn converging to F. So what we want to do is, if you see the notation Fn converging to F, we want to assume they are referring to pointwise convergence, unless it also says that Fn is converging to F uniformly. So we want that piece in there. So if you see Fn converging to F, assume this denotes pointwise convergence, unless otherwise stated. Let's take a look at the pictures associated with pointwise convergence and with uniform convergence, just to try to understand kind of how this would look graphically. So we were saying in this first picture, I've just copied and pasted the same graph that we were looking at before. What we notice is that as x goes to 1, n has to actually go to infinity. So capital N, this is what's preventing uniformity. Because there's no way, we know that when you're dealing with convergence and, one convergence condition requires one capital N and another convergence condition requires another capital N, then you can take the max of those values to make sure both conditions hold. However, if there's a place where capital N is going to infinity, that's telling us there's no way for us to pick a maximum capital N that will work for everything. This is analogous to when we looked at uniform continuity and we said, is there a way to pick a smallest delta that will work for everything? And we said that's not possible when there's a place where delta goes to 0. So the flip side of this in convergence is that we don't want there to be a place where capital N goes to infinity. Otherwise, we won't have uniform convergence. But in terms of a picture, what you're doing is you're fixing your epsilon band your epsilon band is just going around the entire function. And we're saying no matter where you are on this curve, there should be a way such that as long as we are dealing with functions in the tail, so I could draw a bunch of different sequences of functions. Maybe here's one of my other functions, but notice that it's this is I'm going to call this some fn. It's wiggling, but it meets the constraints and it stays inside there. I could have another function in my sequence, that's maybe getting closer and closer and hugs it a little bit better. But the point that we're trying to make here is that every fn with n greater than or equal to capital N should stay in the band, or in the epsilon band, regardless of which x we are looking at.